Okay, here's another example of some channel capacity problem. And in this one, we start with a noiseless channel with a bandwidth of 1 megahertz, and it carries a digital signal with 8 signal levels. And in part A, it wants to know what's the maximum bit rate of this channel in the noiseless case. In that case, we're going to use the Nyquist equation, which says that the maximum bit rate is twice the bandwidth times log base 2 of the number of signal levels. For part B, it says, suppose we want to carry data at half this bit rate. This is a typo here, I'll announce to the class, because the channel isn't really noiseless. What is the minimum SNR required? Give your answer in decibel units. Well, now we have a real channel that's not noiseless, and we're going to use the Shannon equation. And it says that the bit rate, the maximum bit rate, is the bandwidth times log base 2 of 1 plus the SNR, where the SNR is given as a ratio. Okay, so I think I know which equation I'm going to use for each part of the equation. We got a noiseless part and a part with noise. And so let's write down what we're given. We're given the bandwidth of 1 megahertz, RB. No, that's the bandwidth, John. The bandwidth is 1 megahertz, or 1 e to the 6th hertz. And we're also given 8 signal levels. L is for levels. We get 8, and I can plug directly into this equation to get that maximum bit rate. RB is twice the bandwidth times log base 2 of L, which is twice, the bandwidth is 1 e to the 6th, and the log base 2 of 8. And you should immediately recognize that 2 cubed is 8, and so the log base 2 of 8 is 3. And so we have 3 times 2 times 1 e to the 6th, or 6 e to the 6th, or 6 megabits per second. For part A is the maximum bit rate. For part B, we're going to go and say our new bit rate is half of that, 1/2 of the 6 megabits per second, or 3 megabits per second, or 3 times 10 to the 6th bits per second. And we're going to, it says what's the minimum SNR required, and so we need to solve the Shannon equation for the SNR. And I'm going to do that here. I'm going to say it's the bit rate divided by the bandwidth is equal to log 2 of 1 plus the SNR. And now I'm going to take 2 and I'm going to raise it to each of those, each side of that equation. When I go 2 to the log 2 of x, it just turns into x, 1 plus SNR. Okay, that's the property of logs. And now I can solve for the signal to noise ratio. It's equal to 2 to the RB over bandwidth minus 1. And this comes out as 2 to the RB is 3 times 10 to the 6th. The bandwidth is still 1 times 10 to the 6th. And I subtract 1 from all of that. This is 2 cubed minus 1, which is 8 minus 1, or 7. And that's the SNR as a ratio. Now we're going to convert the SNR into decibels by taking 10 log base 10 of the SNR as a ratio. So it's 10 log base 10 of 7. I guess I'll do that on the calculator. 10 times log of 7 equals, now I got the log base 10, yeah, log base 10. Okay, so I'm at 8.45 dB. And so This one's kind of tricky because you have to solve the Shannon equation for the signal to noise ratio here. Hopefully it's not too bad if you know the laws of exponents and logarithms. And so this equation, or this problem, combines both the case of the noisy and the noiseless channel, and it's actually a fairly realistic thing to take the theoretical Nyquist rate based on the number of levels, and then take some fraction of that Nyquist rate and say, okay, realistically we're going to have noise, and we're not going to hit the full Nyquist rate due to signal to noise ratio limitations, and we're going to then use the Shannon equation to figure out what the SNR needs to be. In fact, this is quite a small signal to noise ratio, and so we're able to hit this bit rate of 3 megabits per second quite easily with a signal to noise ratio of less than 10 dB. Okay, so here the signal is only 7 times as powerful as the noise, which is actually a pretty bad case. That's actually pretty noisy. But we can do it in this case because our bandwidth is 1 megahertz. Okay, so this is a realistic example where we have quite a bad channel and we actually don't get that much of a bit rate out of it. Hope this helps.